Hello there. This presentation is on the quantum theory of scattering. We will be discussing some elementary ideas of the scattering problem in quantum physics before we move on to a more rigorous formalism of it. So basically, every scattering process includes a stream of incoming particles, a scatterer, and scattered particles, as shown in figure. One natural scattering process we are familiar with is the formation of rainbow due to the sunlight scattered by raindrops. However, in this quantum formulation of scattering theory, we are more interested in the scattering of particles by potentials. This is because of the fact that a quantum physicist would be more biased towards elementary particles, as they are the one which obeys the rule of the quantum world. Okay, so the incoming particle can undergo two types of scattering. One is the inelastic scattering, in which the state of the incoming particle will be changed after collision, while in elastic scattering, which is the second type of scattering, the state of the incoming particle will remain unchanged after the scattering process. One important thing that we have to do here is that we have to assign a wave function for the incoming particles and scattered particles, because we know that we are treating this quantum mechanically. So wave mechanical formulation has to be used here. But the problem is that we know that a wave function is not a measurable quantity. Therefore, what we have to do is we have to link the wave function to a quantity that can be measured during the experiment. And in this case, that particular measurable quantity is the angular distribution of scattered particles. So our wave function is related to angular distribution of particles that are scattered by the potential, or in other words, the scatterer. Okay, so the quantum theory of scattering is that's not only useful in elementary particle physics, but they are also widely used to understand the structure and properties of atom and nucleus. Popular examples of the scattering process are given here, and you can see that a proton and proton can collide or interact together to form proton-proton plus a pi-0 meson. And similarly, they can interact to give a proton-neutron and a pi plus particle, and an electron and a positron can interact to form mu plus and mu minus mesons. So this is a very complicated case where these interactions are giving rise to the formation of a new particle. So this is basically these are examples of inelastic scattering. But for an elastic scattering, which is the simplest of cases, we are expecting a form like this: A plus B equals A plus B. The particles before scattering will be the same as the particles after scattering. Now let's discuss the various methods used to solve a scattering problem in quantum physics. There are two methods that are widely used. In the first method, we set up a differential equation for scattering of waves, and then we will go for the asymptotic solution. In the second method, the problem is considered to be a transition from initial to final state, and then we will apply the time-dependent perturbation theory to study the evolution of state. Here we are restricting ourselves to the first method. In this discussion, I am restricting myself to the case of elastic scattering, because inelastic scattering problems are very intricate. They are very difficult to solve, and it is not wise to try to solve such a complicated problem without learning to deal with a much simpler case like this. So we know that in elastic scattering, the kinetic energy of the incoming and outgoing particles will be the same, And a familiar example is the scattering of electron by hydrogen atom. Okay, so we are again making 3 more assumptions to make this problem a lot easier to solve. The first assumption is that we are excluding the spin of the particles, the spin of the incoming and outgoing particles. And the second is that we are only considering the non-relativistic case. We are excluding the relativistic effects. And the third and the most important one is that we are assuming a potential of the form V R1 minus R2 as central potential. And we have already seen in the case of hydrogen atom problem how central potential helped us to solve the problem easily. And the use of such a potential will allow us to reduce a two-body problem into a one-body problem. We have already seen that in the case of hydrogen atom. Let's have a look at the arrangements that are to be done to carry out a scattering experiment. Firstly, there should be a parallel beam of particles of mass m and momentum p, which should move towards the target. And there should be the target itself, which is actually fixed, and the target will be a potential centered at the origin. And the third will be the scattered particles, which will be, and these particles will be moving all around the scattering potential. There will be the particles moving in the forward direction, backward direction. Obviously, there will be back scattered particles. So, scattered particles will be moving all around the fixed central potential. Now, let's get ourselves familiarized with the various parameters used to study this problem. The first such parameter is the scattering angle theta. As you see, the incoming particles represented by the long blue arrow strikes on a cubic scatterer. Actually, the size of the shape of the scatterer is not important at all. What matters is the potential. We have a repulsive central potential here. We have assumed a repulsive central potential. And when the incoming particles strike the potential or it is repelled by the potential barrier, then the particles will be scattered. Okay. So the red line here is the path along which the incoming particles would have traveled without scattering, and the this scattered beam here, it makes an angle theta with the red line, the original direction which the particles would have moved in the absence of scattering. However, theta 1 is not the only line along which scattering will take place. There will be a theta 2 as shown here. So particles will be scattered in this direction also, and there will be a lot of directions in which the particles will be scattered. And this is shown in figure. You can see this. Okay, so since the potential is central potential, we know that we are going to use spherical polar coordinates to solve this problem. Therefore, the variation of theta from 0 to pi alone is to be considered. Now, if we trace the sharp points of these arrows, if we trace it like this, we will be getting a semicircle like this. And now this semicircle here, it only shows the scattering along a plane, but we know that scattering occurs in all 3 dimensions. It occurs in all directions around the potential. So we have to incorporate all those scattering components. For this, we need to define another angle phi, which is the azimuth angle. Now, if we rotate the earlier obtained semicircle by phi 1, after fixing the red arrow as rotating axis, we will get this semicircle. Okay, together in a three-dimensional image, this would appear like these two semicircles would together appear like a slice of an apple. Okay, so if we continue with the rotation, we will get many inclined semicircles like this. Okay, and an envelope of this will form a sphere like this, and this is the sphere of influence of the scatterer. So your scattering potential will have an effect on the incoming particles up to this point. So your scattered particles will be covering the entire surface of the sphere, and r is the radius of the sphere, and it is, in other words, the range of the potential, the range of our repulsive center potential, and it is the distance up to which the potential can influence the trajectories of the incoming particle. Okay, so after completing our discussions on these topics, these important parameters, and now the spherical symmetry involved in the problem has become apparent. We are now introducing a new parameter called the solid angle. In scattering theory, the concept of solid angle is very important because it is used to describe the angular distribution of scattered particles. So this is a very important parameter that we are defining here. Now let's get an understanding of the concept of solid angle. For this, first we have to fix theta and r and change phi. Okay, for simplifying geometry, we have inserted the Cartesian coordinates here to get an understanding of how the rotation is carried out, and at the center of the sphere is the scatterer. Okay, and this, you know that this is the sphere of influence of the potential of this scatterer, and so we are now rotating this vector, this vector we are rotating, and the rotation will be done for an angle, a phi value of 360 degree. So it forms a full circle on the surface of this sphere. Okay, so this is your theta value, and this r is fixed. You are rotating it in the theta direction by an angle 2 pi. Okay, so now you are slightly changing your theta value, and your r will be the same, the radius of the sphere, and you will rotate it again by phi equals 2 pi. Okay, so you will get another circle which passes through the surface of this sphere. So if you look at these circles from the top, that is with z-axis as your line of sight, okay, it will look somewhat like this. So you are looking from here. Okay, your line of sight is this z-axis, and you will see a circle like this. Okay, now it's important to determine this distance here, this distance. Okay, for that what we have to do is, you can use simple trigonometry. We can see that there is a triangle like this, and this triangle subtends an angle theta here, and this is r, this is the hypotenuse of the triangle, so which means that this distance will be r sine theta. And if we change this line, if we rotate this line along this circle with center fixed, then we will get a new line like this, and this small change in d phi, this will be this is equivalent to a change of this vector from here to here, and the d phi is the angle between this initial position of this r and this new r here. Okay, so the trigonometric part can be well understood from this triangle here. So if we know this this radius and this angle, then we can calculate this arc here, this distance by which the vector r has moved. Okay, so this will be r sine theta d phi, that is the radius into angle. The next step would be to fix phi and r and then change theta. If we do it for this r, then we will get a circle like this if theta changes from 0 to 2 pi, and for this r we will get another circle. It will be going all around the sphere. And remember that in spherical polar coordinates we know that theta only changes from 0 to pi, but let's let's assume that for now this construction is true, this variation is true, because we are only only constructing the solid angle here, and therefore we don't have to apply the constraints imposed by the spherical polar coordinates for now. Okay, so if we view these circles, these two circles with x-axis from here, if we view it from here, this is your line of sight, then you will find that these are circles like this, and obviously each circle will have a radius r. Okay, the radius will be r, and if we move it along this direction, then you're changing theta. So the very small change in theta is represented by d phi. Now we know that arc, this distance is actually so this is the change of r from here to here. So this distance you are calculating, so that distance will be arc into angle, which is r d theta. Okay, so this area here formed by the intersection of four circles, see this red region, this is the infinitesimally small area ds of the sphere. It is this area which, when integrated, gives you the entire complete surface area of this sphere. Next, we isolate the ds and the volume of the sphere formed jointly by ds and radius vectors. So you have four radius vectors here, one from here to here, and from here to here, and the others from here to here and here. Okay, so here you have a polished triangle. In the previous slide, you might have noticed that these regions were actually slightly curved, and here we are assuming that for a very small area ds, these are almost flat. Okay, so from the calculations shown in the previous slide, we know that the one side of the triangle will be arc d theta and the other side will be r sine theta d phi. So you can directly calculate the volume, that is length into breadth, which is r square sine theta d phi. Now we are in a position to define what exactly a solid angle d omega is. Let's consider a two-dimensional circle which is drawn on your paper. You know that you can determine the angle subtended by an arc of length L and radius R by using the equation theta equals L by R, that is angle equals arc by radius. So let's assume a three-dimensional sphere. So your d omega will be a 3D analog of your 2D angle theta. Okay, so its equation will be a by r square, where a is the area of a small portion of sphere surface like ds, which subtend a solid angle, and r is the radius of the sphere. If you compare these two equations, you can see that here it is in the numerator it is L, while here it is area due to the additional dimension, and here it is R, while here in the denominator we have R square due to compensate for the additional dimension. Okay, so from the previous equation and the equation here, that is d omega equals a by r square, we can calculate the d omega value of our sphere of influence, and this will be r square sine theta d phi divided by r square. This quantity here is actually ds divided by r square. So r square and r square will get cancelled, and you will get sine theta d phi. By defining the solid angle, we have combined both theta and phi into a single parameter. Apart from this advantage, we know that the solid angle itself cannot define the scattering phenomena. It cannot measure the outcome of scattering experiment. So a measurable quantity in this experiment would be the differential scattering cross section, and also we are using another quantity, which is the total scattering cross section. So the result of a scattering experiment will be expressed in terms of these two quantities. First, let's understand what differential scattering cross section is. It simply tells you what fraction of the total number of particles, that is, what fraction of the total number of incoming particles is scattered into a unit solid angle subtended by the area ds. So this is the area ds, and this will be the solid angle subtended, and this is the equation which gives you the differential scattering cross section. This notation can vary from textbook to textbook, and you can see that differential scattering cross section is dependent on theta and phi. So small n will be the number of particles scattered into d phi, and n will be the total number of incoming particles. So this ratio, n by d omega, that is the number of particles scattered into unit solid angle. If this is 1, that is d omega is 1, then this equation will be simply n by n. Okay. So in a scattering experiment, by measuring d sigma, we are actually determining how much of the incoming particles are scattered into a unit solid angle. We can now define the total scattering cross section, which will give us the total number of particles scattered around the center potential per unit time. So this is a very important parameter, very important result of the scattering experiment, and this will be your incoming particles, and this will be how scattering occurs. This is the infinitesimally small area ds, and we have to remember that this sphere of influence of the potential, this will repel the incoming particles. So the scattered particles here, you can see the distribution of scattered particles. They will not be in contact with the sphere. They will be either lying on the surface of the sphere or slightly away from the surface. Okay, so we know that d sigma, which is the differential scattering cross section, gives as the fraction of total number of incoming particles that are scattered into unit solid angle. This essentially means that the differential scattering cross section gives us the number of particles that lies within the area ds. So we are now in a position to determine the total scattering cross section, that is the total number of particles scattered around the sphere. So if you know how much particles are there in this very small region, then you can add these small regions to find out how many particles are there on the surface. Okay, so this is realized by integrating the differential scattering cross section. Integration, you know that this is continuous addition, and once you integrate the differential scattering cross section, that is once you integrate the number of particles, when you add the number of particles in each infinitesimally small ds areas which form this surface, then you will get the total number of scattered particles. So you know that for phi varies from 0 to 2 pi, and theta varies from 0 to pi. Okay, so if the potential is spherically symmetric, then the problem will become a lot easier to solve. This is because d sigma will not have a phi dependence, because the scattered particles are distributed uniformly along the surface of the sphere. That is, if the distribution of particles will be looked upon from this side or top or bottom, they will appear to be the same. That is, there will be no phi dependence, but theta dependence will be there, as this distribution is different. Okay, the theta will change from here to here, and if you look, the distribution is not following any pattern. But if you look from around the sphere, what you see is that your surface will have a distribution like this. Since the integration from 0 to 2 pi will give you a 2 pi, because d sigma will be independent of phi, your total scattering cross section will look like this. Okay, so I will stop here for now. In the next lecture, we will link these parameters to wave function as we discuss the wave mechanical picture of scattering.